Thank you. So before I start, I just want to make an announcement that at 6 o'clock there will be another talk by Chris Braff in room 306. So if you're interested, it's the title is Non-Commutative String Topology and the Cyclic delink Conjecture. So some new work that Chris has done. So I'll hopefully finish on time, and if people are interested, can just move upstairs and listen to Chris. So as Vita said, my title is Relative Shifted Symplectic Structures, and it's a joint work with Dima Rinkin and Bertrand Thoen.
And if I say another title, you will talk about something else?
Say it again? No. But yeah, a long time ago, I was at a talk by Calabi where he had prepared 5 slides. There were these old transparency slides that you project on a projector. And he started talking about something, and then maybe around slide 2 he decided that his original plan wasn't that very interesting. So he switched the topic of the talk completely at minute 10 and talked about something completely different, but kept putting the slides. And since he only had 5 slides, he had to recycle these 5 slides like 10. So it was one of the most surrealistic experiences I've been. So what this thing is about, let me tell you the plan. Hopefully I'll go through everything. So first I'll try to motivate it a little bit by mentioning 2 problems that one can solve by the formalism we're developing. And then so then I'll talk about the formalism, which is defining and constructing relative symplectic structures or shifted symplectic structures. So I don't know how much time I'll have to go into the details of the formalism. It's a bit hairy. So I'll say some words, but then this is in some very big generality under very mild assumptions, and it's very good for theoretical purposes, but it's completely useless for computations. So then I'll spend some real time and talk about a more restrictive case where one can do shift theoretic calculations completely. And this is going to be, again, for constructing and understanding relative shifted symplectic structures, but not for arbitrary families of spaces or stacks, but constructible ones. And finally, I really hope to get to this part to show you some interesting examples and applications of this. Okay, so let me start with the motivation. I want to present 2 problems that can be solved by this story, which are, I think, interesting in their own right. So the first problem is to understand symplectic structures on character varieties, or on character moduli, on derived character moduli spaces. So let me say some words about that, and hopefully when we get to the examples, I will show you the interesting example. So the prototype question, which we understand very well, and which you've probably seen many times, is if you start with X, say a compact orientable surface, topological surface, and say a complex reductive group G, you can look at the most naive topological G invariant you can attach to X, which is going to be the character variety. So I'm going to call it the moduli of representations of the fundamental group of X in G. So this is just the affine GAT quotient of the homomorphism space from pi 1 X to G.
So X maybe has a boundary?
No. Compact, orientable, no boundary. Not yet. Yeah. So if you look at this guy, we know that on the nice locus of this guy, so this some coarse moduli space parameterizing semi-simplifications of representations of pi 1 of X in G, and so it tends to be very singular. Well, very singular. I mean, you know, it has quadratic singularities, but it's normal, so it's singular, but reasonably singular. One thing we know is that if you look at the nice part of that, the smooth part of that, this is symplectic, algebraic or homomorphic symplectic. But we know more, right? I mean, we know that the symplectic form can be described cohomologically. So the symplectic form, let's call it omega, as a pairing on the tangent space at the smooth point. So that's a representation which is, say, reducible, has a risky dense image in G. This thing is given by taking two classes, Xi1 and Xi2, and viewing them from the deformation theory of representations as cohomology classes of the fundamental group with coefficients in the adjoint representation, and mapping that to the trace of the cup product of those two guys integrated over the surface, where this trace is really a killing form. So it depends on the choice of a killing form, but it gives you a skew-symmetric pairing, which then you can do some analysis to prove that is non-degenerate. Well, non-degenerate is actually Poincare duality, but closed is not obvious. And so there are various ways in which you can do the check that this is closed. One is deformation theoretic, which requires work, and then there is another way which describes this open part as a quasi-Hamiltonian reduction for a group-valued moment map, which also describes that form as the form on the quasi-Hamiltonian reduction. And so, yeah? No, it's finite dimensional. I mean, you just write a system of generators with one relation.
Bunch of matrices.
It's finite dimensional. Yeah. It's finite collection of matrices. You just need to write generators with one relation. The moment map is the relation. And so the prototype question is, how do you make sense of this symplectic form, again, cohomologically and intrinsically on the whole of M? And the solution, we know what the solution is. The solution is that you have to correct M You have to get to one of these guys that Roman was talking about. So to extend to O of M, we need to resolve the singularities suitably. And the way that you intrinsically resolve the singularities in this case is by looking at the full moduli problem. So this is replace M by, I'm going to call it log G of X, which is going to be the derived moduli stack of G local systems on X. And again, this is not a mysterious thing. You can construct it explicitly by taking a simplicial resolution of the classifying stack of G, semi-free simplicial resolution, and just taking homomorphisms from that resolution, of pi 1, and take homomorphisms from that resolution into G, and take the topological realization. So this thing is a very concrete thing, and what it is, it's a derived stack. Yeah. So this thing, you know, it builds in. It has a built-in stackiness. So it's a derived moduli, derived algebraic stack. So in this case, it's a one stack, luckily, but you know, you can do the same thing in higher dimensions, and it's going to be a higher derived stack. But it has a great property, which is that
So it's a kind of a semi-explicit simplicial.
yeah, there is a which is locally a finite type. And because it's locally a finite type, that means that its cotangent complex is perfect. No, in higher dimension. When if the space is not a k pi 1, then the stack of local systems has cohomology coming from the higher homotopic groups. And
I mean, somehow if you took the perf version of this instead of G, then your local system is going to be spread out over complexes. But if I took G equals GLF,
yeah.
then the action, even if they're higher homotopic groups, factors through just the high one. Right? So I mean, I think if you fix.
No, but they're higher cohomologies of the local systems, which are not cohomologies of the group.
But that's in the positive direction of the tangent, not the negative direction. Right? If it's GLM, then you're like homology with coefficients and endomorphisms, which is just a local system in degree 0. So all the homology is non-negative. I guess it's not important anyway.
Well, you have to shift by one, right? Yeah, so, but no, he's saying whether it's a higher stack or a one stack, whether it has negative homotopic groups in the tangent complex.
Maybe it's not so important.
Maybe it's a one stack always. No, what Chris is saying is he's saying that for any x, it's going to be a one stack. It's going to have a derived structure with many cohomologies, but the stackiness is going to have only one homotopic group. Maybe. So this thing is perfect, and then on this guy, you can write exactly the same formula. So it makes sense on the tangent complex. And because it just pairs, so you have three cohomologies now, degree 0, degree 1, and degree 2. It pairs degree 0 and degree 2 and 1 and 1. And again, Poincare duality tells you that it's not degenerate. And so the only thing you really need to make sense is what it means for this to be closed. And it turns out it's a little bit of an extra structure. So you need a lift of this guy to the second step of the Hodge filtration in the total complex of this complex, and or to a cocycle there. And there is such a lift, so yeah, so it turns out that, so now closeness of omega is extra structure, which is a lift of omega to a cyclic cocycle. And it exists. And so there is a, what? It's canonical. So there is a canonical lift. It depends exactly on the same data that it depended before. Well, it depends on the orientation of X and on the killing form. And and this actually works in any dimension. So it works for any X oriented compact manifold of dimension D. The only difference is that in that case, the tangent complex is not symmetric around 0. In that case, yeah. Well, Hamiltonian reduction turns out to be part of the, it's a special case of this thing. So can I? So in that case, so this stack log G of X is really, so in any case, it's the mapping stack from X viewed as a constant stack on the side of schemes with this topological space as a fiber to BG. So that's our derived stack. So this is in derived stacks. It has pairing. So it has a closed two form, which is not a degree 0 cocycle in the cyclic complex, but it's a degree 2 minus D. And so it gives you, if you project cocycle to cohomology, it gives you a pairing . It gives you a pairing between close to form omega, which gives a contraction map from the tangent complex of this stack to the cotangent complex, but it's shifted by 2 minus D. And the non-degeneracy condition is to say that this is a quasi-isomorphism. And so this thing exists, and they all exist for the same reason. So the reason for the reason for omega is an inductive process. Bg is symplectic. So this is like a 2 minus d shifted symplectic structure, and Bg itself is symplectic with 2 shifted symplectic structure. Corresponding to a killing form. Any choice of a killing form gives you a canonical 2 shifted symplectic structure. And then there is a theorem, an integration theorem, which is this algebraic geometric version of the AKS-Z formalism, which says that if X is a derived stack which is compact in an appropriate sense with orientation or a Calabi-Yau structure of dimension D, then the mapping, and F is an n-shifted symplectic stack, Calabi-Yau structure, let's call it OR, then F omega is an n-shifted symplectic stack, then the mapping stack from X to F has a canonical n minus d shifted symplectic structure, depending only on omega and on the orientation. And to answer Sasha's question, quasi-Hamiltonian reduction is actually a special case of this statement. I'll tell you later, because but it is, well, it's a special case of this statement and one other statement which I'll actually need, so let me formulate it. So this is one way to construct new symplectic guys from old ones. And there is another way to construct new symplectic guys from old ones.
But what is the O is compact? If derived stack such that what?
So there is some compactness condition. It's called O compact. With an orientation. I'll actually talk about in a moment about the orientations in more details.
O compact means O is compact. Is that yeah? Could you just comment?
No, it doesn't mean that O is a compact object. Yeah, no, that's not what it means. It means that the integration against the orientation gives you a perfect pairing on cyclic chains. And the integration against that gives you an equivalence of Holmes. It gives you duality on the category. So, yeah, it just says yeah. This means that OR realizes a third duality on X. But let me just say the other theorem. The other theorem is that if F omega is n-shifted symplectic, so these are all theorems that we proved with Bertrand and Michel Vaquy and Gabriele Vesozzi. So if you have an n-shifted symplectic stack, and there is a notion of Lagrangian. So two guys that map here that have Lagrangian structures. So again, Lagrangian is, or isotropic is a structure here rather than a property, because in order to say what isotropic means is you have to have a map between stacks such that the pullback of the symplectic form is homotopic to 0, so you need to choose the homotopy as part of the data. And Lagrangian is saying that that homotopy is non-degenerate in the right directions. So if you have two Lagrangian maps, then the derived fiber product of the derived intersection of L1 and L2 inside F is n-1 shifted symplectic. Which is not a very surprising statement. So there are two homotopies that realize the Lagrangian structures for these guys. You need to take their difference, and the non-degeneracy will tell you that on the fiber product that will be a symplectic structure. But so these are two mechanisms for constructing these symplectic guys, and so if you use those two, you can see that the quasi-Hamiltonian reduction is actually both Hamiltonian and quasi-Hamiltonian reductions are special cases of these two guys. But say it again? To a combination of the two, yeah. So this is going to give you the moment map reduction, and one of the targets you have to construct by. I'll show you that. So where was I going? I was trying to motivate what we want to do. So what I want to say is that what we want to do is we want to understand the character varieties in the case when the Riemann surface is, or the variety that we're dealing with is open. So now on the same type of answer or structure for the moduli of local systems, geolocal systems on a smooth but not necessarily compact X. And so already for surfaces, this question, so again, on the smooth points of the moduli space, of the coarse moduli space, there is an answer which is classical, or maybe not that classical, but say 10, 15 years old, but very explicit and nice. And you would like to understand what happens with it when you go to the singular points. And then you resolve by the derived stack of local systems again. And so in this case, there is something very interesting happening. The space of all local systems on X is not symplectic, but is Poisson. And in order to understand the symplectic cliff, you have to fix data at infinity.
So X now is just any manifold?
Yeah, non-compact. So we need to fix data at infinity to understand, to fix a symplectic cliff. And already for surfaces, this is interesting. So there are two types of things you can do. You can look just at the topological things, which are representations. So this is like you're dealing with tame representations of the fundamental group. So if X is a surface, looking at log Gx, so this is derived moduli of representations of the fundamental group in G, And so this guy has symplectic leaves arising from fixing conjugacy classes of the monodromy on the boundary circles. And this is a special case of the previous two constructions. So what's happening is that if you look at the boundary circles, so you have the restriction of local systems on X to local systems on the boundary. This is just a union of circles. Circles are oriented one-dimensional manifold. So this thing is one-shifted symplectic. By the mapping theorem. This turns out to be Lagrangian. And fixing the conjugacy classes of the monodromies on the boundary is also Lagrangian. And so the guys with fixed conjugacy classes, which is the intersection of those two, this is zero-shifted symplectic. As you expect. So this is what happens in the tame case. And in the wild case, and so, okay, so this again has this question has a version in higher dimensions, and in higher dimensions it's much more interesting. So if you take X to be an algebraic variety and the boundary to be normal crossing, then prescribing monodromies along the boundary divisors is not necessarily it's not enough to give you a symplectic leaf. There is a constraint on the monodromies, which is a very interesting constraint, which is purely group theoretic. And we still don't understand. So we know what the constraint is. We know how to characterize these local monodromies, but we still don't understand why.
What do you mean when you say purely group theoretic?
It's purely group theoretic. So if you have two components intersecting, then you have two group elements which commute. You cannot take arbitrary commuting elements in order for the thing to be symplectic. So there is a condition on the group elements. It's sufficient. In fact, in most cases, we can prove it's also necessary. I think it's always necessary and sufficient. So the condition is, we call it strictness. So I'm not going to write it, but let me just say, if the elements are nilpotent, it's exactly the condition of Ginzburg on a principal nilpotent pair. I'm saying let us be at the intersection of two components. No, you have elements. This is really for elements. Yeah, you really need to fix the elements, because there's some jerks on the boundary that you need to trivialize. It's really for elements. But in any case, so there is this condition, and so what's really interesting is what's happening with the irregular guys in higher dimensions, and that's our first motivation. So this is the tame case. So you can take Stokes G X. So this is the moduli of wild representations of the fundamental group of given a fixed irregular type. At infinity. So I don't know if I have time. I really want to do this example. I don't know if I have time to do it. So I mean, later on when I tell you what the statement is. But the point is that, you know, if you take flat connections with irregular singularities, say even on the disk, they're described still by topological data, but the topological data is much more refined than the monodromy. So that topological data in its most compact form corresponds to two pieces of information. And this topological data, let me just say, is completely determined by the irregular type of the flat connection, which is just the Laurent tail of the connection at the pole up to conjugacy in the loop group. So if you fix flat connections with a given Laurent tail up to conjugacy in the loop group, that Laurent polynomial determines two pieces of topological data. One, it determines a constructible sheaf of finite sets, in fact, of partially ordered finite sets on the circle. And then for any flat connection with that given irregular type, you can look at the convergent flat sections of bounded growth, and it turns out that the local system of flat sections on the circle for that connection is filtered by that sheaf of finite partially ordered sets. Filtered by flat subbundles which are labeled by that sheaf of partially ordered sets. And so the irregular type is just this sheaf of partially ordered sets. So this given irregular type, this given irregular type, I'm going to call it F. So this is going to be some local constructible sheaf of maybe I shouldn't call it F. Maybe I should call it L for labels of maybe lambda of posets on the circle on the boundary. You can do it at any. I mean, so it's for each boundary component you get one guy. Yeah, but they're stock sectors on which you have a well-defined ordering, and then they're points at which the ordering changes when you cross them. So it's really partially ordered. The circle is stratified. Okay, so let me say it. So you have the circle. The circle is broken into pieces by the Laurent tail. On each, so you have now a constructible sheaf of finite sets on the circle. As a sheaf of sets, it's actually locally constant. But as a sheaf of partially ordered sets, it's not. So on each arc, it's totally ordered, linearly ordered. And the order at each point where two arcs meet is the minimum of the two orders from the two sides. So that's actually the condition on that sheaf. That's what you get from a Laurent tail. And then what you're looking at is you're looking at local systems of with structure group G on the circle. Yeah, so this was for GLN. I just did it for GLN. But the whole thing actually works for arbitrary groups, and I'll tell you what the data is for arbitrary groups. For GLN, you have a local system of vector spaces, of n-dimensional vector spaces on the circle, which is filtered on each arc is filtered by flat subbundles, constant subbundles labeled by that partially totally ordered sets. And the condition is that at each point, when you look at the filtration coming from this side and the filtration coming from this side, they have a common splitting. A common splitting. There are two filtrations on the same vector space. They have to be simultaneously split somehow. And then there is a global condition on the filtration which says that if you pass to the associated graded to that filtration by constructible subsheaves, that's actually a local system on the circle. And so this is the entire data of these guys. This is what they are for GLN. And so if you look at these guys and you look at the moduli of them, so they're like local geolocal systems on the curve, on the surface, which are decorated by this. So there is the irregular type gives you this labeling on the boundary, and they're decorated by some filtrations on the boundary labeled by this labeling. And again, you can ask, is that symplectic or not? And it's not. It's Poisson again, but a symplectic leaf is selected by fixing formal monodromy at infinity. So here we were fixing the actual monodromy. Here you have to fix the monodromy on these associated graded sheaves. So the point is that, you know, your irregular singular guy, you can make it regular by a formal change of variables. Maybe going to a covering of the circle. And so the monodromy for that regular guy is what you need to fix. And again, this on the smooth points has a construction due to Phil-Bouch in terms of quasi-Hamiltonian reduction. In fact, in this case, the situation is better than what it was in the previous case, because if you choose your irregular type generically, there is a stability condition on irregular types. So if you choose a stable irregular type and a generic formal monodromy, then the moduli space of stock structures actually, the derived moduli stack of stock structures is in fact not stacky and not derived. It's nice and smooth. But if you don't choose them generically, then they are stacky and derived points. And in fact, if you don't choose them generically, it could be stacky everywhere and derived everywhere. So you still have this question of how you write a symplectic structure. So okay, that was the first motivation. I don't have time for the second motivation. Which, I mean, the second motivation is actually also interesting. I just wanted to advertise this paper of Shende and Takeda, where they look at a version of this which is non-commutative when they look at mapping stacks from categories to the stack of perfect complexes. So the stack of perfect complexes is again shifted symplectic, and if the category is Calabi-Yau of a given dimension, depending on whether it's proper or smooth, then you have to take either a right Calabi-Yau structure or a left Calabi-Yau structure, which is a theory that Chris and Toby Dickenhoff developed. And so if you look at these constructible shifts of categories with relative orientations, you can pass to the global sections of those constructible sheaves and look at perfect or pseudo-perfect complexes depending on whether you're in the proper or the smooth case. And what Vivek and Alex proved is that these guys are shifted 2- d-shifted symplectic. And one of the motivations that I wanted to mention is that there is one case which their theorem doesn't cover, which is coming from the fact that if you have a constructible sheaf of categories and you compute moduli spaces along the fibers, so you get a constructible stack of moduli, and then you get global sections of that, that may not be the moduli of perfect complexes or pseudo-perfect complexes in the global sections of the sheaf of categories. So the passage to moduli of perfect or pseudo-perfect complexes and the passage to global sections do not always commute. So they do commute for co-sheaves of smooth categories, because global sections are given by co-limits, but they do not commute for sheaves of proper categories. And so the theorem of Vivek and Takeda, it gives you a 2 minus new shifted symplectic structure on the moduli of objects in the global sections. But you also have, if you have a notion of relative symplectic structure on a sheaf of stacks, you have a global symplectic structure in the sections in the moduli stacks. And those are actually more. So, okay, I'm not going to write anything about it. I'm not going to say any more. But so you get a little bit more if you do it relatively and then pass to global sections. Okay, so let me. What do I have? 15 minutes with you? What is it? 15 minutes. Okay, so. Sorry, I mean the motivation took way too long. So one thing that you notice immediately, so here is the problem, so relative symplectic structures. So if you want to understand the forms, the closed forms or the forms along the fibers of a, so the setup is we want to look at X is a topological space, so I'm going to say for now Hausdorff and locally compact. And then you have some sheaf of stacks, sheaf of derived stacks. I mean, you have to say stack of stacks, but it's becoming, so I'm just call them sheaves. So sheaf of derived stacks on X, say over C. I mean, it's over any base ring of characteristic 0, but let's say over C. You want to understand closed forms on F may be shifted and you want to understand non-degeneracy of closed two forms. And one thing you notice is that, so you whatever you're doing, you would want to get this guy as an object at least defined on X, and the covariance property of this is that this is a complex of co-sheaves of vector spaces on X. So in particular, the non-degeneracy of the closed two forms will have to involve Verdier duality on X. And so you need Verdier duality for, I mean, in this context, for Hausdorff locally compact spaces, and luckily you have it, and it is a duality between sheaves and co-sheaves. And so you can work with dualizing co-sheaf. And of course, you know, instead of sheaves, you can, in principle, look here at forms with coefficients in any co-sheaf that you can choose, and then you can shift that complex in co-sheaves. Okay, anyway, so you can take this primordial form of Verdier duality, which apparently, so I always thought, you know, it was written up for the first time by Lurie, and it is in the higher algebra book, but apparently it was already in Verdier's notes, so Verdier duality, which gives you an equivalence of sheaves and co-sheaves. Yeah, the Verdier duality functor is just the compactly supported cohomology, yeah. And the dualizing co-sheaf is just the image of the constant sheaf under Verdier duality. And so you can do this with stacks, and so I don't have time to explain any of the technical details, but let me just tell you the theorem. So using Verdier duality, of sheaves on X with co-sheaves on X, we can define these guys. And we can define, I'm not going to talk about arbitrary coefficients, and we can define a non-degeneracy. And then the main theorem tells you that this commutes with push forwards. So the main theorem says that if F is a proper map between locally compact Hausdorff spaces, and F is a sheaf of derived stacks, and omega is a relative symplectic of degree n, then you can push forward the sheaf of stacks and you can push forward the form, and it stays symplectic. Again of degree n. There is a condition on the stack for this to make sense and to work, but it's a very mild condition. The condition is that, okay, I'm going to just say it is locally formally representable. So that means that at each point is given by a formal moduli problem, by a DG Lie algebra. And so it's a very, very mild condition. You can put, more complicated representability conditions which are still preserved by this, and they're useful, but I'm not going to talk about that. And say it again. Shifted by n, yeah. The shift doesn't change, yeah. The shift is the same. And so what I want to say is that you can actually do calculations here. So yeah, in the case when you're not dealing with a random calculations.
What happens if you take the constant sheaf of a point on the two manifold and push it forward?
Say it again.
You take like a constant sheaf, the point mod, the BG.
Yeah,
over a smooth manifold and push it forward.
Yes.
What do you get?
You get the sections of BG along the fibers.
In other words, maps from that manifold.
Yeah, map from the fiber to BG.
Yeah, so it's a shift.
No.
Map from manifold to BG is just
No. But these are. This is a symplectic form on the fiber, on the stack. There is no shift, so we'll talk about it later.
I'm confused about the content of the theorem and why is it point?
Say it again.
I'm confused about the content of this theorem and why is it point?
Yeah, so when y is a point, it says that you have a stack of globals. Yeah, so if you have a sheaf of stacks on X, you can look at the stack of global sections of F.
Yes.
And if you have an n-shifted symplectic form here, relative, then the push forward of that form, which is the global section of that, is again an n-shifted symplectic form here.
And the stack
Independently of what X is. Independently of what X is.
Independently of what X is, because the way the shift is defined is it takes into account the dualizing co-sheaf with its natural dimension.
I mean, I'm probably missing something, but suppose that this is a trivial family. Suppose that your F is X times something.
Yes.
Then times some fiber. Then global sections just maps from X to this fiber.
Yes.
And then it should relate to something you said in the beginning about, but then.
No, right. But I didn't tell you what the definition is on a relative guy. The definition of.
We want the definition.
Yeah. There is a definition of what the guy is, and it uses the dualizing co-sheaf. And so there is a shift by the dimension built in there.
And in
Yeah.
fact,
So if you do it in terms of shifts, then stuff will happen. Sorry. So I'm not going to be able to say anything about the. So let me just say in calculations, you look at the restricted situation when X is nicely stratified. So finite and conical stratification, and F is constructible sheaf of stacks. And now you're in the stratified situation, you're doing with stratified sheaves, so you can do Fourier duality with sheaves only. And so I really don't have time to explain this, but the point is that you can do nearby cycles for specializations of strata, for co-specializations of strata for this stack. And the co-specialization maps from the value of the stack on a stratum to its nearby cycles are very nice, and once you write down the condition of what the form is and what non-degeneracy is, so again, there is in this language you can write what the form is, and you can say what it means for the form, what the closed form is, and you can say what it means for that form to be non-degenerate. But now everything is described in terms of the exit path category. In fact, twisted arrows in the exit path category. So you're looking at functors from the twisted arrows in the exit path category to stacks. So for each of those guys, you have a stack. And the condition for a symplectic form turns out to be, so let me just give this definition, which turns out to be equivalent to the definition there. A symplectic form on F, relative symplectic form, is the data for each alpha in the labeling set of the stratification of a relative n-shifted symplectic form. On F, for each alpha, which is the guy okay. sorry. Let me say it right. A form omega, which is a close to form on this stack, and now I'm going to take values in the dualizing complex shifted by n. So that's my n shift. Sorry, kx is non-degenerate if two conditions hold. So for every alpha in the labeling set of the certification, we have, first of all, that okay, I'm going to say omega alpha bar. So this is the induced form on the nearby cycles for the stack F. So I'm going to denote this by F alpha 0. So these are the nearby cycles for the stratum alpha. If the induced form is, let me get now the dimensions right, it's m plus 1 minus the dimension of the strata shifted symplectic. That's condition number 1. And condition number 2 is that if you look at the specialization from the stratum to the nearby cycles, so there is a map, co-specialization map going from F alpha to the nearby cycles. This map is Lagrangian. And that's for every alpha. So that's the condition, and turns out it's equivalent to this definition. And it's actually something that you can use to do calculations in a very efficient way. And I'm really out of time, so I can't tell you about the examples. But you can do everything. You can recover everything from this. You can recover the mapping stack thing. You can recover the Lagrangian intersections from this push forward statement. You can recover. You can do these Deligne-Lagrange stock shifts. So they are given by some very explicit stacks over the surface, which I could tell you about, but I'm not gonna. And again, the modulo F stocks data with a fixed formal monodromy is a Lagrangian intersection, and it gives you, it's a push forward like that, and it gives you a symplectic structure. And the great thing about it is that it actually works in higher dimension too. But the stock structures in higher dimension are much more complicated. So describing that sheaf that you can write down on the surface purely combinatorially, so it's not combinatorial in higher dimensions, is something that you really need to write explicitly. And this type of description helps because if you want to check that something is symplectic, it actually turns out that you only need to do it in one level. And after that, it's automatic. So sorry, I don't want to go over time, so I'm going to stop here.
So it's not, let's